Hello guys, welcome back to my channel Gamma Digamma, and in this video I am going to let my friend Brandon from the previous significant video, if you remember that, it was about introduction to what is an algebra. So he's gonna make a second video following that first one, so please check that out if you haven't already, and let's get started.
Hi guys, today we're going to show that you can't multiply vectors in 3D. There's no way of doing that. To start, we'll actually show why there's no unital associative real division algebra with dimension 3. And we'll show why that's equivalent to saying that there's no way system for um, multiplying vectors in 3 dimensions. So first of all, what is a unital associative real division algebra? Well, we defined what an algebra is in the last video, so you should go to watch that if you don't know. And we also defined the terms unital and associative. Unital just means there's an identity element, and associative means that multiplication of vectors is associative. And what real means is that the vector field of this algebra is a field is over the field of the real numbers, which just means that you can only multiply vectors in the vector space by real numbers, like scale them by real numbers, I mean. And division algebra just means that every non-zero element of A has a multiplicative inverse. Meaning for all x in A, right, we have the element x inverse, where x inverse x is equal to the identity vector, which is also equal to x times x inverse. Right. And now we will begin by first examining this map. L L sub x from A to A, right? Where L sub x of y equals xy. And so this is a map where you have a fixed vector x, but then the input parameter is y, so it takes the vector y and then just multiplies it by x on the left side. And this side is pretty important because we didn't say that A is commutative. And we're going to show that this map is actually linear in the variable y. To do that, we just plug in Lx of c1 y1 plus c2 y2. Right. By one of the axioms of algebras, the axiom of distributivity, we have that this this is equal to x times c1 y1 plus c2 y2, and we just use distributivity to say that is equal to this. Right. And then we use the axiom of homogeneity to move this scalar c1 these scalars C1 and C2 to the left-hand side. And we can see that this is nothing but C1 Lx of y1 plus C2 Lx of y2. And this shows that the function Lx is actually a linear function, which means that we can actually represent the map as a matrix. And this matrix will be filled with scalars of the field, which is in this case real numbers. And suppose that the vector space of A has an odd dimension, right? So we say Lx of y. Now we're making it clear that y is a vector. It was a vector previously. This is just notation. So Lx of y is equal to this matrix filled with these entries m 1 1 all the way through 1d d1 d, where d is the dimension of the vector space associated with A, our algebra. So Lx of y is just this matrix applied to y, right? Furthermore, the entries are real numbers because this vector space is actually over the reals. Now we see that we want to find some eigenvalues of this transformation, right? So the way you find eigenvalues is to take the characteristic polynomial and find its roots. And the how you find the characteristic polynomial, you just subtract lambda off these diagonal entries. And you take that determinant. Then, what do you get then? Well, you actually get a polynomial of lambda of degree d. So this first coefficient is actually, since d is odd, then you multiply it out and it's negative 1. So negative lambda d plus c1 lambda d minus 1 plus c2 lambda d minus 2 dot dot dot, and you have c d at the very end. And what do we know about this polynomial? Well, it's an odd degree polynomial, so it must have at least one real root, right? And you can see this by, you can use the intermediate value theorem or any number of techniques, because you could also like look at the asymptotic behavior. It's like it must be like positive as lambda is very like goes to minus infinity, and negative as lambda goes to infinity, so there has to be a point where it crosses 0. Anyways, we know of the existence of one lambda such that the characteristic polynomial determinant of this matrix, we'll call it m minus lambda I equals 0. Right. So now what we can do, because the determinant of this is 0, we know that there has to be at least one set of vectors such that the matrix, this applied to the vectors is equal to 0, right? All we're saying is we can find at least one eigenvector. We'll call the eigenvector gamma m equals lambda gamma. But what is m gamma? This is just the matrix applied to y, which is equal to Lx of y, which equals to xy. And so now we have this expression, this relationship. And what can we do with it? We know that okay, so all we're saying that is that the kernel of this matrix is not trivial. Therefore, we can find at least one vector, we'll call it gamma, such that m gamma equals lambda gamma. In other words, gamma is an eigenvector for the matrix M, therefore an eigenvector for the map Lx. Right? We have that m gamma equals Lx of gamma equals x gamma. Right? We have this relationship now. So what can we do with this relationship? We know that gamma is non-zero. So this is an eigenvector. And because we're working in a division algebra, we can find an inverse element for gamma. There's this an element called gamma inverse, such that when you multiply gamma inverse and gamma, you get the identity vector. And we can just multiply this on the right-hand side. And since it's associative, we don't really have to worry about the brackets. So we say this is true. We have this is the identity. We'll call the identity E. Right. And on this side, we have it's equal to. Sorry. Right. Meaning that lambda E is equal to x. But what is telling us? It's telling us that no matter what x we have, x must be a scalar multiple of the identity vector, right? X is equal to lambda E. But then we can't have the vector space be more than one dimension. And why is this? It's because, say, we had like a three-dimensional vector space, for example, or any odd number of dimensions, and we have our basis vectors, or any two like linearly independent vectors. We'll call it x1 and x2. What this relation tells us is that x1 equals lambda 1e and x2 equals lambda 2e. But then it's obvious here that x1 and x2 are not linearly independent because they're related by the coefficient. We have that x1 is divided by x2 equals lambda 1 over lambda 2. So x1 is equal to lambda 1 over lambda 2 x2. So they're not linearly independent, right? So that shows that our vector space has to be one-dimensional because it's the only dimension where this relationship holds true for all vectors in our vector space. So the conclusion is A is one-dimensional. And as a side note, you should it's like you learned in linear algebra that if A is one-dimensional, it should be isomorphic to R. So we're really saying that A is sort of the same thing as R1. Right. What have we just shown? Well, if we have A, this specific type of algebra where you can multiply vectors together, but you can divide vectors as well, and among other stuff, we show that if A has an odd dimension, well, the dimension has to be 1. Therefore, it can't be three-dimensional, right? Now, I said I was going to show how this is equivalent to saying that there's no system to multiply vectors in 3D. This is what I mean, because if you want a good system to multiply vectors in 3 dimensions, your system should have all these good properties, like in addition to multiplication, you can divide vectors. There's like an identity vector, and your multiplication should be associative, right? But we just showed like in 3 dimensions there is no system for multiplying vectors, and this is actually the reason why Hamilton invented quaternions. Well, he was trying to create this system in 3D, but after a lot of frustration, he realized he couldn't do it. He had to actually go into 4 dimensions, which led to the development of H, the set of quaternions. And this will be a topic for a future video, so stay tuned. And I hope you guys enjoyed that.